If you've ever seen a field of modern wind turbines, you've probably noticed something: variation. Indeed, there are some key differences between different turbines to know. There are also some key similarities to know. Let's start with those. The first is that they are all big. Even in the smallest cases, we're still talking about 50-plus meter high structures. And sitting on top of these giant towers is a unit the size of a large school bus called the nacelle, which houses the generator and gearbox, with enough space for technicians to work in comfortably. Another similarity is in how they work, via a series of rotating shafts. First, the wind hits the blades, which spin and turn the main shaft. A series of gears will then translate the slow, powerful rotation of the main shaft into a much faster, rotating secondary shaft, which then spins a series of magnets through wire coils. This is what generates electricity. When it comes to differences, there are two big ones to pay attention to: the size of the blades and the maximum capacity of the generator, called the rating. The largest turbines are rated at over 15 megawatts, enough to power more than 10,000 homes. Smaller turbines might be rated at 0.5 megawatts, enough to still power several hundred homes. Larger blades, which can be longer than a football field, cover more windswept area, and that means more captured wind energy. Generally, keeping a larger generator at full capacity will require larger blades. Of course, the exact choice of blade and turbine will depend on the wind speeds at a given site. The goal at any site is to build highly utilized turbines, often measured via the turbine's capacity utilization factor, or CUF. A turbine running at full capacity for an entire year would have a capacity factor of 100%. And since wind speeds vary all the time, optimizing the capacity factor means chasing a moving target. The relationship between wind speed and a turbine's power output is described by the turbine's power curve. When wind speeds are too low to turn the rotor, no power is generated. At a certain speed, called the cut-in speed, power production begins. As the wind speed increases beyond the cut-in speed, so does the power output. Eventually, the power output will approach the turbine's rating, its capacity. This is the Goldilocks zone. As the wind speeds increase further still, the capacity of the generator will be exceeded. To mitigate this, the blades will need to be angled or pitched out so that they capture less wind. If the wind speeds continue to increase, eventually the blades will need to be completely pitched out, bringing the blades to a full stall. This is called cutting out. The power generation drops back to zero. The upper limit of the curve is set by the generator rating. The shape of the curve, on the other hand, is set by the size of the blades. Larger blades have a higher cut-in speed. It takes more wind to get them to spin. Once spinning, however, they will produce more power and approach the turbine's rating at much lower speeds. In other words, a larger blade creates a steeper curve. It fills the capacity more quickly. The benefit of this is higher utilization. There are, however, downsides to larger blades. The first is that, at higher wind speeds, larger blades are more likely to cut out. More windswept area means more power captured, means more possibility of overloading the generator. The second is that larger blades suffer more wear and tear, which will significantly reduce a turbine's effectiveness over time. This is not a small consideration. Wind hits the blade like a lever. Longer blades are longer levers, and this means more torque on the system. Smaller blades capture less energy from the wind. As the wind speed increases, they will fill the capacity at a slower rate than a larger turbine would. Put another way, they lead to a flatter power curve. This means lower utilization. The upside is that smaller blades bear less wear and tear and are less likely to cut out. Generally speaking, a small generator will be paired with smaller blades, especially at higher wind speed sites where larger blades would lead to cutouts. However, this isn't always the case. If wind speeds are low and predictable, and cutouts are less of a concern, larger blades can be paired with smaller generators to boost utilization. The ratio between the generator size and blade size is called the specific rating or specific power. Turbines with bigger blades and smaller generators are described as low specific power or LSP turbines accordingly. The overall trend in recent years is bigger and bigger turbines, both in blade size and rating, if the conditions allow. The economics are generally more favorable in this case. However, the specific choice of what turbines to use is a complicated decision, made as part of the design of the overall wind park and based on more factors than the wind speeds alone. Next, we'll explore these wind park level considerations.